Hello, class. I am actually only setting up for my second lecture today, although I might do another one in a little while. I have to turn my timer on. See, I'm getting so good at all these things. Of course, you know, by the next one, I'll have forgotten it all and everything else. And I have increased the brightness, so although I don't know, it seems to not be, I don't know. Anyway, I increased it and it was nice on the last one. I think it works out. It's working out pretty better. The autofocus thing off, I think, is helping too. So it seems to be better than it was anyway. Now, what I want to do is I want to do the derivation of the determination of a voltage at any location around a two-wire transmission line, right? And that's what we're really looking at here. Is we've got two uh, lines of charge, and for that, you know, I'm just you know, it's a transmission line. That's what you should think. You look up when you're driving along the freeway, you see those transmission lines. This is it. So I've got a negative, you know, one there, and I've got a positive metallic conductor over here. I didn't mean to make that little slash on the paper there, but whatever. Now, I mentioned before, and I'm gonna make this so it seems I think more intuitive to you. I'm gonna make this plus 5 volts, and I'm gonna make this minus 5 volts. And so if that's the case, 3, 4, 5, 6. Oh, thank God it was 6. That means that right down the center here, we have that virtual ground, don't we? So right in the center, we have the ground. Now, the distance that I have perpendicular to this going out to the positive point is going to be S. And the distance from the negative one to this middle virtual ground line is also going to be S. But then I want to look at some other point in space, any other point in space. All right. So I'm going to say that it's this point in space right there. And then I'm going to say that we have a distance here of R1. So the distance from the positive line of charge to that point in space, let's call it point A. A gets all the attention, doesn't it? Right, Q hardly gets any attention except when you're talking about charge. Now, that distance there from the negative electrode over to this random point in space. Let me, you know, it's random. Because I'm saying that because, of course, what I'm trying to do is come up with a general formula for any point in space so that we can get a profile of what the voltage, you know, scalar field looks like. And we could generate the scalar field voltage from this equation. Yes. Isn't it great? Isn't it great being an engineer, scientist? That's right. It's great. Now, if you remember before, I said that if you were looking at a line, if you had just one line here, right? Let's say you just had one line, and you were looking at different radii away from that line, R1 and R2, right? And you were looking at it. In fact, I think I have that derivation right back here. Let me just pull it up for you. I can, where was that? No, well, I've gone back to, oh wait. Yeah, here it is. Okay. So if you had two different distances, it would be the voltage differential between here and here is going to be equal to the density of the, I'll put rho sub L now that we're sort of using rho sub L for linear density, and then rho sub S would be surface density, and rho sub V would be volume density, volume of charge density. So anyway, getting back to this equation from what the derivation that I did a long time ago was rho sub L divided by 2 pi epsilon sub 0, right? And then multiplied by the natural log of R2 over R1, right? And that would basically give you the voltage. I should have gotten rid of that negative a long time ago. That would give you the voltage differential from here to here with this minus this, because this is the larger voltage, right? And this is the smaller voltage. So when I'm looking at R2 over R1, that's going to be a positive value then from this. This is my line right here, right? That's my line going into and out of the board, and that's where rho sub L comes in, because that's the charge density on this line. And then, a distance R1 away from that line, I'm going to have a relatively high voltage. And then R2 out here, I'm going to have a lower voltage. The further I get away from that line, the lower and lower the voltage is going to be, right? So if I'm subtracting R1, a voltage at R1 from voltage at R2, that's going to be a positive number. And that's why I've got the natural log of R2 over R1 and everything else. Now, let's get back to this, right? Let's get back to this, because if you look at it, you'll see that R1 and R2, like for instance, if I look at this, I see that if I was to draw R1, right, in a circle around that transmission line, R1 would be a little bit less than S, right? And then if I looked at R2 and I looked at the radius of R2, around that line, it would be a little bit more than S. Right? Doesn't really matter if it's more or less. It's going to tell us if it's positive or negative or whatever, right? So here's what I've got, and that's what I've got there, that difference there. So in order to find out how R sub 1 and S, compare, and then over here, R sub 2, I better write R sub 2, R sub 2, R sub 2 and S compare, we can come up with an equation or a derivation that's going to do it. Now let's just look at the positive line first. So V, I'm going to say sub positive, because this is the voltage that we're going to find just from the positive line. We're going to do a separate one for the negative line of charge. But first, let's just do one for the positive line of charge. Then we'll do one for the negative line of charge. Then we'll impose these over each other to get the total line of charge by adding them together. Doesn't that make sense? All right. So the positive voltage for the voltage profile for the positive line of charge is going to be rho sub L over 2 pi epsilon sub 0. I'll say epsilon sub 0. We could just say epsilon, but I'll say epsilon sub 0. Because we're working in air, I'm assuming that we're working in air. And then that's going to be from R2. Wait, what have I got? R. Oh, I'm sorry. I'm making that R2, and this is going to be R1. So R2 is from the positive line, and R1 is going to be from the negative line. All right, that's good. Because that fits in with my drawing that I have on my notes. So R2 to S, dr over r. And of course, we know that that is just the natural log, dr over r. The integral of dr over r is just the natural log of r. So what we end up getting is we end up getting the density, the linear charge density, divided by 2 pi epsilon times the natural log of S over R2, right? Now, when we look at the negative line of charge, first of all, we know that we're going to have the same charge density, but it's, instead of it being positive, it's going to be negative, right? So I've got negative rho sub L over 2 pi epsilon sub 0 times the natural log. Actually, that's let me put this. That's the natural log of S over R1. Hey, wait a second. Let me check something. Just a second. I will be right back. Am I still recording? Oh, I'm recording. Well, oh my God. Oh, well. I thought I'd stop the recording, or no, I'm still recording. Okay. No, this is all right. I mean, I hope I didn't take too long, but I was just looking at it for a second. I thought, God, it seems like something's wrong here, but no, nope, everything's right. I just went through the rest of the derivation and just checked it out to make sure that everything came out fine. All right, so my total V then from the two different contributions that I've got there is going to be my V plus, right, plus my V minus. And so I end up getting rho sub L over 2 pi epsilon sub 0 times the, I'll do it in two steps here, times the natural log of S over R2, right, minus the natural log of S over R1. Now, I think everybody knows that if I have the natural log of A minus the natural log of B, that equals the natural log of A over B, right? Just like the natural log of A plus the natural log of B equals the natural log of A times B, right? Sorry about that. Or the natural log of x to the n equals n times the natural log of x, right? And all of those, just sort of keep those in your skill quiver, and you can pull them out anytime you want. There's other ones that are good too, to change natural logs of different numerical base systems, and I could write that one down for you. I think I might have already taught that one to you though, but Sometime if I have time, maybe I will. Or maybe I won't. I don't know. I just, you know, how many times does it come up now? It doesn't come up. Whereas things in class, I can be writing these things down. It brings this up, and then I can go off for like 2 or 3 minutes and do that. I'm not even sure how much time I've got left. Where's the director? Yeah, so it's 20 minutes left. So I might have time to look at that if I have place left on here. Let's get back to this because I've got several things that I want to do. and I'm just saying that this is what I've got here, and so that makes it simplify, doesn't it? So I've got rho sub L over 2 pi epsilon sub 0. And then I've got the natural log. Now, what do I really have here? Let's look at that. I've got S over R2 over S over R1, right? So we can simplify that. So that's rho sub L over 2 pi epsilon sub 0. The one that's in the denominator of the numerator is going to stay in the denominator, right? That'll move down to the denominator. And the one that's in the denominator of the denominator will flip back up into the numerator. And so what we end up getting is the natural log of R1 over R2, right? Does everyone see how that works? Okay. So that is the equation for you know, a 2-wire transmission line. But now here's what I want to do. I want to look at a particular point. I'm going to look at a point that is 1 meter, right? When we originally set this up, well, actually, I'm not even sure if if in the last lecture I did tell you what the distance was between these. But this is the same as the distance before. This is going to be 1 meter in between here, and this is 1. I did put that underneath there, didn't I? Yeah, I did. And this is 1 meter. I know the help, you know, the video help, the gophers. I'm the gopher. Gopher, get me that coffee. Okay. So, this is what we get for the total voltage. But what I wanted to do is I want to do a little example problem so that we look at one location. I want to look at a location that is just 1 meter down from here. So if that's 1 meter, that's 1 meter. I'm going to say 1 meter down from here. I'm going to call that point B. All right. So that's point B. And I want to find out what the voltage is at point B. So let's do that. So the voltage at point B, we'll just use our little equation here. Oh, I forgot to give you the thing to it's 1. The line charge density is going to be 1 microcoulomb. All right, 1 microcoulomb. So I've got 1 microcoulomb, just looking at the equation over here, divided by 2 pi times 8.85 times 10 to the minus 12 farads per meter. Now, you know, if we had a relative permittivity, we'd have to put that next to it, wouldn't we? So I'd have to put that over here, but we're not. We're working with air. Air is almost the same as outer space. I mean, really, I should be putting 1.0004 in there, shouldn't I? But I'm not going to, because it's almost 1. So we treat air and we treat outer space the same as far as this goes. All right, so we've got that, and then we want to multiply that by the natural log of R1 over R2. Well, let's look at what that is. Now, we know that R1, now where did I use? I think it was R2 was the positive, R1 was the negative, so R1 is going to be minus 1 meter, right? So we're going down 1 meter. So the natural log of 1 meter over, and then R2 now, going from here all the way over to here, what is the hypotenuse of that triangle? Let's use the blue to show the hypotenuse. So what's that distance, right? What is that distance? Well, you know, we could say that side's 2, so that's 2 squared plus 1 squared, that's 4 plus 1, that's 5. And the square root would be the square root of 5. That's what this would be. The square root of 5. Is that what I got? No, what are we talking about? 2 squared? Yeah, that's what that would, why did I think that for some reason, wait a second, am I drawing that right? That's 1, 2, 3. Yeah, where is my calculator? 2 squared plus 1 squared is 5, square root of 5. 2.236. 2.236 meters. I'm saying that because for some reason I wrote down before that it was something else, and I'm looking at it right now and I'm thinking, well, that looks like 2 meters and 1, and that's 1 meter. That's 2, that's 1. It's gotta be 2.236. So it also tells me that I have to recalculate my thing here. So let me just tell you what I'm doing. I'm doing the natural log of that ratio there times 1 microcoulomb divided by 2 divided by pi divided by 8.85 exponent minus 12. And that gives me minus 14,471 volts. And how odd that is not any. Oh wait, no. That's that would be very similar to what I had. Okay, yes. So there you go, minus 14,471 volts. Now the moral of this story is, if you've got 2 high power lines, do not be 1 meter below them. Do not be 1 meter below them, because then even different parts of your body are going to have different huge voltages. I mean, you're going to have thousands of volts between just your head and your feet, right? Could you imagine shorting that out? Yeah, God, don't do that. So don't ever climb the power line pole. That's the moral of that story. Okay, now that is an example of that, and we also did the derivation of that. So that we can sort of put behind us now. Now what I want to do is I want to look at electric flux. And so really what we looked at up here was we looked at the voltage in the voltage field for a 2-line of charge scenario. That's a fancy word. All right. So There we go. And now what I want to do is I just want to look at electric flux, and I want to talk for a few minutes on electric flux, really a conceptual thing of electric flux. And to do that, I'm going to draw my now relatively familiar capacitor, right? I love to draw the capacitor because the capacitor is pure isometric drawing, right? Everything's going at 30 degrees. Maybe it's supposed to be 45. I don't know. Am I drawing it at 45? It looks like more like 30. So I've got two different plates here. I'm going to take this plate, and I'm going to say that this plate is 0 volts. And I'm going to say that this plate over here is 200 volts. Now, don't worry. And it's got a line coming out of it, right? And it's in a circuit. It's in a circuit. So I want you to stare at that capacitor, because I'm going to mention something, and I think I probably mentioned this before. I don't know. I taught you engineering mechanics, so why would I ever bring this up? But I mention it in every network theory or circuit theory or whatever, course, applied circuits or whatever, analog, that anything I can teach. I always like to bring this up because so many students live in the, is that coming through good? Yeah. So many students live in the delusion. It's a delusion. And here's a good joke. What's the difference between a delusion and an illusion? Everybody gets to see an illusion, but only one person gets to see a delusion. Get the joke? Anyway, I thought it was funny. So a lot of people are deluded into the fact that they think that when you close a circuit, let's just look at a circuit here, right? Just a regular DC circuit that's got some type of resistor to minimize, the current flow and everything. And then here is my capacitor. Now, let's say, I didn't draw that right. Let's say that there's a switch, right? Let's say that there's a switch in the circuit. Now, after I turn that circuit on, what does the current look like? What does the current look like in the system, right? There's going to be current as soon as I throw that switch. I've got this battery here. Let's say that's a 10-volt DC battery, and I've got an uncharged capacitor, right? As soon as I throw that switch, what does the current look like? Is the current at time equals 0 plus, right? The instant after I throw that switch. Is there no current in that circuit? Or is there the same amount of current as would be in a short circuit? Now, you've all had network theory 1, which is really where this is from. So you all know that the answer is that it's just like a short circuit, isn't it? When I look at the current, as soon as I throw that switch, the current in this circuit is going to flow just as if there was no capacitor there whatsoever, right? As soon as I throw that switch, this is so important. You've got to know what I'm saying. As soon as I throw that switch, there's going to be current flowing through this circuit, right? In fact, the current that's flowing through that circuit is just going to be V. Let me give you this. This is 10 ohms. There you go. So it's V over R, isn't it? So the current flowing through there is 1 amp, just like a short circuit. As soon as I throw the circuit, that switch, the current flowing through that circuit is just like a short circuit. Now, you're probably saying to yourself, well, how can that be? How can that be? Because at no time, never Not before I throw the circuit, not after I throw the circuit, not if I flip the circuit back and forth over and over and over and over again. It doesn't matter how many times I do it. Never is there one electron that travels across that capacitor. No current, I shouldn't say current, I should say electron. No electron ever passes from one side of capacitor to the other. No electron ever crosses those plates. Ever, ever, ever. Unless you have a breakdown, of course. Right? Never does. The charge builds up, right? Let's just look at this for a second here. Let's say I throw that switch. Now, I guess I shouldn't say 200. I should say 10, just to keep with my little circuit over here. But let's say that I throw that switch, right? Now, I've got this backwards. Maybe I should do this. Maybe I should say, just so that it looks the same as here. Maybe I'll say this is the 10 volts, and I will say this side is the 0 volts. How about that? That's my 0 volts. Now, because it's the same way as the circuit I've drawn here. That's what I'm saying. Now, once I throw that switch, right, all of a sudden, immediately, I've got 10 volts, right? Immediately that I throw that switch, I've got 10 volts on this side of the circuit. I've got 0 volts on this side of the circuit, right? Does everyone see that? So I've got this. In fact, this over here would be connected to ground, wouldn't it? So I could get electrons, in there. So anyway, I've got the positive side here. So what's that going to do to the electrons in the copper on this side? Isn't it going to start to pull the electrons in this direction? It's pulling the electrons out of the copper on this plate. I'll call this plate X. It's pulling the electrons out of the plate, and where is it pulling them to? It's pulling them to the positive electrode, isn't it? And here's my positive electrode, right there. Here's my negative electrode, and that's grounded, right? So it's pulling them this way. Now, once the electrons start leaving this and start flowing in this direction, of course, that's opposite to the conventional direction of current flow. But once the electrons start leaving this and start heading over here toward the battery, what are they doing? They're taking the electrons, they're making this more positive, aren't they? So they're making this side more positive, they're making this side more negative. And so you could say that the positive, or the electron holes, are going in the opposite direction this way. So I could say that the electron holes are going in that direction, or I could say the electron holes are going in that direction, right? Electron holes. But really, what are electron holes? They're just electrons going in the opposite direction, right? So we would have electrons coming out of the ground and coming up to here to replace those electrons that are on the other side. So that's what we're doing. We're replacing the electrons because of the polarization of the two plates that we have here, right? We're polarizing, and we're creating an electric field inside between these two plates in this dielectric, and that's causing the electrons to flow in here. So it appears that there's an electron flow, there is a current flow. So that's what I want you to know. There is current flow. Right? But no electron flow across that gap. No electron flow. Well, I guess our time is up. I wanted to talk about flux, and I'm going to, but it'll be in the next lecture. All right, and I'm sorry for that thing. I thought that I had paused it, but I guess not.